but because here we have voltage drop VE, so with our voltage drop across RE in parallel with R2. Okay, now we need to use Thevenin to reduce the circuit. So what will happen, this supply will be short, and this resistance and this resistance, they are in parallel, and if we look from here for R Thevenin, they are in parallel, we got the equivalent. And if we want the voltage drop here across then we use voltage divider rule. This resistance times this voltage on the addition of the two resistances, as we learn in voltage divider rule. Now the circuit reduced in this way. I think now you remember what we did with the ammeter bias. It was here it was RB. Now it become R Thevenin. Just the only difference in the names. Otherwise the same procedure could apply, and we have the same formula. You see the difference between this formula and the formula used in ammeter bias is here it was VCC, now it become V Thevenin, and here it was R Thevenin, it was R base, and that's it. The same procedure apply. Example. Now he asked me to find VCIC, which is the point of operating point, quiescent point. Okay, first of all I will find R Thevenin. It means this resistance and this resistance in parallel. I got it. Next I will find E Thevenin. Voltage drop across this resistance found by voltage divider rule, as you can see here. I got it. Now I find IB. We have the formula, we just need to substitute. We got I base, multiply by beta, we got I collector, and then we go to find V collector ammeter, similar to the ammeter bias circuit. Another circuit. Again, we change the values, but the procedure is the same. R Thevenin, E Thevenin, I base, V collector, I collector, V collector ammeter, and that's it. If you want to find more, as example, VC, VE, VB, as we discussed before in ammeter bias, VC is VCC minus ICRC. We have all of them, we got them, and then V ammeter equal I ammeter, R ammeter, and we have the value for I ammeter. Here I can add both IB and IC, or I can ignore IB because it's small. Usually we focus on IC. And V base is V ammeter plus V base ammeter, as we discussed in ammeter bias. Now for voltage divider bias, but approximate analysis. What we do in approximate analysis, this circuit or this analysis could be applied based on fulfilling the following condition. What the following condition say? Beta RE, okay, greater than or equal to 10 R2, 10 times R2. Beta RE greater than 10 times R2. Okay, it means if this happen, beta RE is greater. What does this mean? If this one is high, we can assume that the current here will follow most of it here, so they are in series. Okay, and this means that this voltage point here, VB, equal the voltage drop across R2. So R2 VCC over R1 R2. Now also V base ammeter will be VB minus VE. So we got V ammeter, and if we got V ammeter divided by R ammeter, we got IE, which is the same ICQ by approximation. So when the resistance RE, if we multiply it by beta, become greater than 10 times R2, then we can apply approximate. Let's repeat the same previous example. Okay, I will come to check. Beta it was 140, RE it was 1.5, and R2 was 3.9. Multiply them, 210 kilo ohm greater than 339 kilo ohm. Yeah, we satisfy condition. Then we can apply. Step 2. Now I come to find VB, R2 VCC over R1 plus R2, and then VE, VB minus V base ammeter, which is 0.7. I found VE. I divide by R. I found IE, which is the same IC, and since I found IC, I can find anything I want in the circuit, as we discussed before. You see, VCE I can't find it because I got IC. Now another example, repeat for the previous example discussed in exact, but repeat it here. Let me check. By the way, let me check the output for the two examples when I apply for the same example, exact analysis or approximate analysis. See IC and ICE. Have a look. In exact 0.85, 0.86, almost the same. The approximation is acceptable here. And for VCE 12.2, 12.0, so it's also acceptable. Okay. Now let's take another, the previous example discussed in exact, and we apply here approximate. Okay. R Thevenin 55, R emitter 2, I base, again we substitute to find I base, IC by multiplying by beta, we got it, and then VCE. Let's compare. You see, beta, it was 70, then it become 140. When we apply, we can see that ICQ is the same, it is not changed, which means that we get the stability we are looking for. Now let's take another example. He told me that determine the level IC, VCE for voltage divider configuration. We know because they are for resistance, using exact and approximate, and compare the solution. Let me start with exact. I found R Thevenin, R1 and R2 in parallel. Then I find E Thevenin. Then I go to find IB as we discussed before. Then IC. Then VCE as we discussed. Now next, let's go to the approximate. In approximate, beta was 50, RE was 1.2, R2 was 22. When I multiply them, 60 kilo ohm is not greater than 220. So we did not satisfy the condition. Okay, you may say, okay, let me apply even if it is not satisfying the condition. Okay, I will apply the approximate and see the difference. Is it okay, acceptable or not? V base emitter, as we discussed, we got it. Then we go to V emitter, then I emitter, which is ICQ, then VCE. Let me compare. The same example, analyze using exact, we got ICEQ in this value and VCE this value. We apply approximate, even that the condition is not satisfied, we find this IC and this VCE. If we want to find the difference, it means subtract and divide to find the difference and multiply by 100%. The difference will be 23% difference, and here 17% difference would tell me that approximate should not be used here because we did not satisfy the condition. Now again, back to saturation. You see here VCE equals 0. And then the same previous equation discussed for emitter bias is applied here. Now one more circuit, the fourth circuit, which is DC bias with voltage feedback. In DC bias with voltage feedback, as you can see here, what I will do, we will connect RB rather than into VCE, we will connect it into VC. And this means that if I come to find the equation for input circuit, which is on the base, output circuit on the collector, see the difference. Now current will follow from VCE through RC. Now RC become part of the input circuit, then RB, then V base emitter drop, then RE. So when I use Kirchhoff voltage law, I wrote it, we can see that RC is become part. Okay, and actually what happened is IC dash, which is the current here, okay, equal IC plus IB, okay, and since IB is small, we can assume that IC dash is IC, and this will help here, okay. So I rewrite the equations becoming this way, and then the final way is I base equal V collector emitter minus V base, which is the same, numerator is the same for fixed bias, for emitter bias, for voltage divider bias, and for DC bias with voltage feedback. RB here, but beta now multiplied by RC and RA. RC become part. Now the remaining is the same. We find I collector by multiplying beta by IB, and we find V collector emitter, and so on. V collector emitter, as you can see here. Now the voltage drop here plus the voltage drop here, the voltage drop here, which is similar to emitter bias and for resistance divider or voltage divider bias. Okay, the same equation as you can see here. Now let's take example. He told me this is DC bias circuit. I know this is voltage feedback. Okay. He gave me everything I need. He gave me the resistances, he gave me beta, and he gave me the supply voltage. Now I base, we just need to substitute. You see RC is still here. We got I base, multiply by beta, we got I collector. Then VC, if I want to find the voltage here, it is 16 minus a drop here. So just substitute, we got it. Now here it's worth to mention that till now we are discussing emitter bias circuit. It means when the emitter connected to the ground, similar to this one, as you can see here. Sometimes emitter connected to the collector, okay, or to the base. Okay, the same discussion could be applied. The principles is the same. Here I gave you exercise. Okay, I advise you to solve it with the steps. This is using the graph to find RB and RC. Another exercise using the circuit directly to by calculation to find IC to find R1 and RC. Now let's take another example on this circuit. This circuit, you can see it is voltage divider circuit. He gave you the voltage VCC 24, IC, beta, VCE and VE, all of them are given to you. Okay, he asks you to design voltage divider bias network using this information. What is missed here? You can see he wants R1, RC, R2, RE. He wants this value which give ICQ and VCEQ 8. Okay, you know you have application. You want to amplify signal. Let me say in this circuit you want to amplify the signal 110 times, as you can see here. Okay, and the operating point should be here. So you need to select your resistances and use the standard values approximately available in the market. So I will come first. I will say RE. Okay, RE, because he gave you here VE is 1 over 8 VCC is VE over IE. Okay, now IE is approximately the same IC, and VE is 1 over 8 VCC, which is 24 over 8, which will give me 3. I got the phase resistance RE. RE has been found. Now let's come to RC. RC is VRC, the voltage drop here between this point and this point, divided by the current follow through it. This is ohms. And RC is VCC minus VC. And VC is VCEQ plus VE. Okay? Now let's substitute. We have VCC. VCE is given in the question here, 8. V emitter, I have it, 3. IC, I have it because this is I emitter. Then I got the second resistance. Now let's go to the third R1 and R2. We know that V base equal V base plus V base emitter. V base emitter is 0.3 and here is a 3. We got the voltage. Now V base is R2 by voltage divider rule, VCC over R2 plus R1. We have VCC, we have R base, but in this equation we have two unknowns, R2 and R1. We cannot solve it. We need another equation. But we can use for stability situation the formula would say beta RE greater than 10 times R2. Okay, we have RE, we have beta. Can we find R2? Yes, we can. We got it. Now let's take it back here and here to find R1. We substitute, as you can see here, we got R1. Now we go to find values close to these values. As example, in the market, we don't expect that we will get 41.15. We may find 42 or 43. We write 42 or for something close. You got it? This is another example, another exercise. I advise you to solve it at home. Okay. Now, so for design, you need to find the resistances R1, R2, R base, R collector, and R emitter. Some of the tips could be used here, advising to be used that V emitter typically it is in the range of 1 over 4 to 1 over 10 from the supply voltage VCC. Okay, you can use this formula, or V in general 1 over 10 directly VCC. Another exercise I advise you to solve based on the same previous example discussed. For switching, now a transistor, as I mentioned, BJT, could be used in active region as amplifier, as a variable resistance to amplify signal, or in cutoff and saturation region as a switch. This to be discussed in power electronic in level 3. But just here I would like to mention that we deal with the transistor in ideal situation as a wire when it is on, conducting the full current, and the drop is 0 because the resistance approximately 0 or equal to 0. This is ideally. And it's open circuit, the voltage is high and the current is 0 because R is infinity. This is ideally. But what happened, and this is how we deal with it, when it is open circuit, the voltage across it is pulse, and when it is 0, when it is short circuit. Okay? But what happened exactly is it did not happen that directly from 0 it jumped to the full voltage or full current. No, it takes time to increase in this way. You see, exponentially. Now 10% of it is the delay time. We call it delay time. It needs some time in microsecond, okay, to reach 10%. And from 10 to 90 it is rising time, and from 90 to 100 time it's called separation time. Okay, so it takes time, but we approximated to make it as square directly, I mean instantaneously from 0 to full load current. Now how we in the lab, how we make sure that the transistor is working? Do you remember we mentioned that before, that we can represent the transistor by two diodes, either in these directions or in these directions, okay, because NPN and PNP. And since it is two diodes, then we expect from 3 terminals that 2 of them only will have short circuit. Example, if I measure here and here, okay, this is usually the voltage across the base emitter, 0.7, okay, 0.7, germanium 0.3, but most of the transistor available today is silicon base. If I measure between collector and emitter, between this point and this point, it's supposed to be 0, okay. And if I can measure, it's like measuring this diode. It's we have short circuit in one direction, as example here, and open circuit in the opposite direction. The same thing here, short circuit in this direction, opposite circuit in this direction. Between these 2 points there is open circuit all the time. Okay, let me stop here. We will continue in the next model.